Yes, everybody, welcome again to the second talk of this afternoon session. And the speaker is the Dr. Simon Locke. I want to say a few words about Dr. Simon Locke. If I know I said something not entirely correct, please correct me. He did his undergraduate in Cambridge, right? And after Cambridge, he went to Harvard and to do his PhD. And there he studied planetary science, in particular the modeling of the lunar origin impact. And then he and his advisor, Sarah Stewart, found something very amazing. So we will hear from him. Now he's a postdoc at Caltech. Are you still at Caltech because you were telling me that you'll be moving away?
Yes, so I'm at Caltech for another week and a half, and then I will be moving to the University of Bristol.
Okay, you're back to
for a fellowship.
Okay, good. Yeah. All right, good. So we're lucky that we catch him, still in the United States. All right, Simon, here's your time. Please start.
Of course. Great. So hello, everyone. It's wonderful to be here. Thank you so much for the invitation. So today I'm going to tell you, as a sort of a story, I suppose, a little bit about the formation of the Earth and Moon and the new idea that we have for exactly how the Moon and the Earth formed. Now, so if you have any questions during the talk, I have the chat open. Just pop them in there. I'll try and answer them as we go through. If I don't notice and it's a burning question and you don't understand what the heck I'm saying, please feel free to interrupt. As much it's, I know how boring these Zoom things can be sometimes. You can get really zoned out. So any engagement is great and really encouraged. Anyway, so before I start, I just want to give you an idea of how I approach this sort of problem and sort of what is the basis of my research. So my research interests are the formation, structure, and particularly early evolution of planets. And the really sort of big overarching question I try and answer in my research is, why is the Earth unique? Why is it so different from the other planets we have in our solar system? And seemingly, though, different from a lot of the other planets that we're seeing around other stars. And the approach I take is to use a mixture of numerical and semi-analytical calculations to try and understand different processes that are happening during planet formation and evolution. And particularly trying to link the geophysics, so the physical process, and the geochemical processes, so that we can try and understand what those sort of physical and chemical mechanisms actually mean in terms of what we see on the planet today and in our meteorite collections and in the samples that we study from the Earth and other planets. And I've covered a whole range of different topics. And obviously today I'm going to focus on just one of those and look at the study of giant impacts and the formation of the Moon. So let's go back to the very start. So Planetary Science 101. Planets form by collisions. So the whole of our solar system started off as a disk of gas and dust. And by some processes we don't actually really understand very well, that dust coagulated into asteroid-sized bodies that then collided together to form sort of planetoid-sized bodies, planet-sized bodies. And the final stage of this sort of evolution, which happens in slightly different parts in different parts of the solar system, is also known as the giant impact phase. And that's when planet-sized bodies collide together. So in our solar system, we think that you basically start off with a whole collection of Mars-sized bodies, and they collide together to make sort of to assemble the final planets. And it's this last stage of evolution. It's called the giant impact phase of evolution. And giant impacts are incredibly dramatic events. So one of the wonders of working in the field that I do, and particularly with the timing of the 50th anniversary of the Apollo missions, we had the wonderful pleasure to work with some people at the Adler Planetarium and the University of Illinois to actually try and come up with a visualization. So this is actually taking data from one of our simulations and sort of visualizing it, and to make it try and give you an idea of what one of these giant impacts would look like. So what you're going to see here is actually an Earth-sized planet, roughly Earth-sized planet, that's actually just rapidly rotating. So it's sort of squished because it's already rapidly rotating. And you will see, if you can't see it yet, an impact that's sort of about the size of Mars, sorry, about half the size of Mars, will come and hit the planet, and you will see the drama that unfolds. Probably not got a good frame rate going. Sorry if there's a little jolty on the screen. But yeah, so you have these collisions. They release a huge amount of energy. For an Earth mass planet like this, more energy is released during the impact than from the surface of the sun. So the whole thing gets really messed up. This is not a good day to be a planet. Most of the planet is melted. A large fraction of it is actually vaporized. This is not something we really think about very much. But if you take rock and you heat it a lot, it does what everything else does. It vaporizes and forms this sort of very extended, sort of can be tens, 100 or more times the size of the original planet. This sort of gas extends very far out from the planet. And so you leave the planet hot, vaporized, and very rapidly rotating. And so giant impacts like this really play a key role in shaping the properties of the planets. They control the mass, the composition. Obviously, I've talked already about sort of the thermal and rotational states. You can also get rid of atmosphere and your volatiles make up your atmosphere and oceans. You can gain those same elements. It's a period where we end up sort of having core formation, which sort of sets a lot of the chemical structure of the planet, including for us, the availability of things like rare earth metals. And it really does sort of set the scene for the subsequent evolution of the planet. Now, giant impacts have a particular soft spot, should have a particular soft spot in your heart, because they have a particular significance for Earth. And that is that we think that it is one of these giant impacts, probably the last giant impact the Earth experienced, that actually led to the formation of our moon. And the idea is, in this very dramatic event, you have these two bodies, they come, they collide, and there's material that is spun off into orbit. And it is out of that material that the moon formed. And so the moon forming impact sort of really set time zero for both the moon's evolution, but also the Earth's evolution. So it's a really significant, pivotal event in Earth's formation. Now, for a very long time now, there has been a sort of a canonical impact for impact idea that sort of controlled the size and style of the impact. And this model was sort of based on three major constraints. We're physicists, and so we do fundamental laws. So the idea was that you had to have your conditions on your simulation effectively was that you had to reproduce the present day angular momentum of the Earth-Moon system, because as you know, you're taught very in your physics 101 class, angular momentum must be conserved. You also have to reproduce the mass of the Earth and the lunar disk. We'll talk a bit more about that later. And also, as we were just being told, we've got the moon has a small iron core, and so you also need to somehow get metal into orbit around the Earth in order to produce that metal core. And it was found in a series of numerical simulations, largely by Robin Knupp, and she's really a giant in this field. There's actually quite a very narrow range of impact conditions that can actually reproduce all three of these constraints, and that is you need a sort of roughly Mars mass impactor, about the escape velocity, and an impact angle about 45 degrees. This is actually fantastic because this is a very logical impact to have happened in the solar system. As I mentioned before, we expect the giant impact phase to start with a load of roughly Mars mass bodies. So great, we should have a load of Mars mass bodies around. Just above the escape velocity is the most common impact velocity, and a 45-degree impact angle is basically the most common impact angle that we expect. So this is made a lot of sense. It was great. It was a wonderful idea. But there's a lot of complicated elements that go in from taking that material that's ejected in an impact, and in the simulations, because the simulations we run only run for about 48 hours, so we never actually form a moon in those simulations. You end up sort of calculating how much mass and material is injected into orbit, and then you sort of stop, and you have to pass off to some other simulation to actually form the moon. And there's a lot of uncertainty about how such a hot, vaporized system such as the lunar disk should evolve, and there's a lot of uncertainty in those dynamics. But as people sort of improved our understanding, it became obvious that there were certain problems with the canonical impact. There were certain aspects of the Earth-Moon system which weren't very easily explained by the canonical impact. So the first of these is actually sort of one of those principal constraints, and that is the fact that the moon is a very large large fraction of the mass of the Earth. Oh, I've just seen there's a question. So we'll come back to this in a second. So I have a question for, saying, how come the proto-Earth looks like an ellipsoid before the giant impact in the animation? So that's because in that particular simulation, the pre-impact Earth was actually rotating very rapidly. So we actually expect towards the end of evolution, because of all of these number of different impacts, that actually most planets will be rotating very rapidly. And so for an Earth-sized planet, there's work by Kakuba and Genda, I think from 2010, although I believe they may have had a more recent paper, that basically looked at that. And for an Earth-mass body, the average rotation rate is between 2 and 3 hours, in the sense that your day is 2 or 3 hours long. And actually the Earth, if you assume that the Earth-Moon system has conserved angular momentum over time, the Earth would have started off with a rotation period of about 5 hours. So if you went back to 4.5 billion years ago, the Earth had just formed, you would have a day that is 5 hours long. And actually it's the tidal recession of the moon that has slowed the Earth's rotation. And so if you went back in time, the Earth at that point wouldn't have been quite as oblate as shown in that video, but it only needs to spin a little bit faster for it to end up looking that oblate. So that's the origin of that. Cool. Cool. Nice break. Come back to the story. So yes, so we're gonna, as I was saying, the canonical model is great. It has done us done a wonderful job of matching some key observations, but there are some, and I'm going to talk about 3 principal ones that the canonical model actually sort of struggles to explain. And the first of these, and probably most significant, but also least talked about, is that the canonical model struggles to produce a moon that is a large enough mass. So of all of the planet moon systems in the solar system, the moon has the largest mass fraction, apart from Pluto and Charon. But as we can, Pluto is no longer a planet. We don't have to talk about that. It's more of a companion. But in terms of, particularly in terms of an impact generated companion, the moon is huge, 1% of the mass of the Earth. And it's actually really difficult to get that amount of mass into orbit. And the way that we try and determine the mass of the moon that we formed out of giant impact simulation. So we simulate the impact itself. We look at what mass is in the disk. And as I mentioned before, the simulations we use to actually calculate the impact are not really suitable for calculating the subsequent evolution. So you then have to choose a model to connect the mass and distribution of material that you have put in orbit to the mass of the moon you expect it to be formed. And the way that it is traditionally done is using what we know as n-body simulations. So these are simulations that take up all the mass of the disk, divide it into little mass clumps, and let that system evolve under gravity. So it sort of basically ignores any thermodynamics. It just assumes that everything is liquid, and you look at how quickly it accretes. And basically, this sort of comes down to an element of mass conservation. You end up with the moon, and the mass that can't fit into the moon gets pushed out back to the Earth or ejected from the system. And let's see if I can get a pointer going. Nope, I cannot get a pointer going. So sorry, come back to that. So if we take the range of giant impact simulations that have been published and look at the mass of the moon that you would predict based on these n-body scaling laws, what you see is that the satellite mass here in masses of moon, so you want to be at 1, basically, right, one lunar mass, that most impacts that we find using these scaling laws actually produce a much larger than a lunar mass. So that was great. So that was the basis of sort of testing our different impact scenarios, was that they produced a large enough mass using these n-body simulations. However, as we've begun to understand a little bit more of the complex dynamics of the lunar disk, we actually find that lunar formation is a lot less efficient than we thought. You actually end up with a lot more mass that ends up going back onto the Earth in order for you to form the moon. And so using one example simulation, this is a set of simulations by Sam and Knupp from 2012. Actually, if you take the collection of published moon formation models, actually only, I believe, one actually produces a greater than lunar mass moon. And so as we add more sophisticated physics to our disk models, what we're finding is that that means mass into orbit in order to be able to form a large enough moon. And so really the canonical impact is very fine-tuned to get as much mass into orbit as possible, and it may be that that is not actually enough. So this is one sort of less talked about but quite significant barrier that we have to overcome with lunar formation. The second observation that has not really been reconciled with the canonical model is the fact that the moon is depleted in what we call moderately volatile elements. So these are elements that you wouldn't necessarily consider to be moderately volatile on Earth. They're things like potassium and sodium, which tend to vaporize at 1,000, between 1,000 and 2,000 Kelvin. But this has been well known since the days of Apollo. This is taken from a paper from Ringwood and Keeson in 1977, that if you plot the amount of different elements in the moon relative to the amount of those elements in the Earth's mantle, you end up with a really great match. That things like magnesium, aluminium, calcium are very similar between the Earth and the moon, but everything that's a little bit more volatile than sort of potassium can be quite significantly depleted. So when we get down to some of germanium, for example, you've got 100 times less germanium in the moon than in the Earth. And this depletion pattern has for a very long time been interpreted as meaning that the moon formed in a very high temperature environment. And actually Ringwood and Keeson, with a not the greatest physical model to support it, but actually made what we think is actually the right suggestion, that the moon, if the moon was formed as an incomplete condensate, which means that if you take a vapor, you only condense some fraction of that vapor and take that material to form the moon, that sort of would explain this depletion pattern. Actually, it's one of those things, nothing is new in science. So 40 years later, when we come to try and tackle the same problem, we actually find that's a very good solution, and just put a more realistic physical model on top of it. But the degree of this depletion is not really consistent with what we observe from the canonical impact. And so there's been a wonderful attempt by Robin Knupp in 2015 to tie the conditions of moon formation to the conditions to the bulk elemental composition of the moon, but that's doesn't really work in the canonical model as far as we understand it. So that's two. The third is probably the one that has really obsessed the field, and it's been sort of called the isotopic crisis. And this is basically the observation that the Earth and the Moon are very similar in a wide range of different stable and radiogenic isotopes. And the reason that is significant is that if we look at all of the different meteorite groups, we find that they each have a unique fingerprint of various different elements, things like oxygen, titanium, calcium, chromium. And so, for example, here I'm showing you what's the cap delta 17O. So this is a way of basically expressing the difference in oxygen isotopes. Too far. And this is a different element of showing different oxygen isotopes. But what you pay attention mostly to the y-axis. But you see Earth by definition here is at 0. And you have Mars. All of the Martian meteorites have an offset above Earth. Angrites, which is the nearest, we call achondrite, so rocky mantle-like body, has something below Earth. And then eucrites, which is thought to come from the asteroid Vesta, again have a different oxygen isotope. And if you look at all of the different isotopes systems, you find that basically there are not very many meteorites that look like Earth. So we'd expect the thing that hit Earth, which is often referred to as there, would have a different isotopic fingerprint than the proto-Earth itself. However, what we find in our simulations, and what we find in the simulation of canonical impact, is that most of the Moon, most of the material that goes to make the Moon, is from the thing that hit us. So logically, we would expect that the Earth and the Moon would have different oxygen isotope fingerprints and different fingerprints and different isotopes. However, that is not what we see. What we find is that the Earth and the Moon have almost identical, to the point that we're actually now really like arguing over whether these two bars, so this blue one being the Earth and the orange one being the Moon, whether these two different values are at all distinct, or whether actually that within error we can actually tell the difference between the Earth and Moon, which is incredible because over time we have got so much more precise oxygen isotope measurements, and yet still the Earth and Moon seem identical. And actually the problem goes beyond that, because it's not, the isotope fingerprints like oxygen are signatures of where material has come from in the lunar disk. But we also look at different isotopes, things like tungsten. And now tungsten is not, well, certainly the 182 tungsten, which is what we're going to talk about, is not a fingerprint of where material came from in the disk. It's actually a radioactive or radiogenic clock of core formation, because tungsten typically goes into the core of bodies during core formation, but the radioactive 182 tungsten is actually produced by decay of 182 hafnium, which likes to stay in the mantles. So depending on when you do your core formation, you end up with a different signature of 182 tungsten in your mantle. But when we look at the Earth and the Moon, we find that the two are very similar. And actually the difference between them is just, it's probably just a function of the material that they have accreted over time, because the Earth is larger, and so the Earth has accreted a little bit more material since the Moon formed. And so this very small offset is probably due to that. And so when they first formed, they had nearly identical tungsten isotopes. And this is really surprising. No one was expecting this. Well, I mean, probably people were. But I was certainly was not expecting this. This is actually fantastic, because it means that what we're seeing is that the Earth and the Moon formed out of the same material. And as I said, because in the canonical impact, most of the material for the Moon comes from the Earth, there's a really big inconsistency in our models. Sorry, most of the material that forms the Moon comes from the impact that comes from there. There's a real inconsistency. We'd expect the Moon and the Earth to look different, but they actually look the same. So these sort of are three really key challenges to overcome, and have really been a sort of a focus of research for the last 10 years or so. Well, more than that. But it has been, as I said before, this last one, the isotopic crisis, this has really been the main focus of the field. And there have been a whole range of different solutions that have been proposed, none of which have really been well accepted. So the first one that was an argument that was originally made by Stein Jacobson and has been taken up by Nicolas Defar, is that can we just explain this whole thing by just saying that the impactor and the target, so both the proto Earth and Theia, just came from the same area of the disk, or at least had eaten the same diet of disk material, and so looked similar enough. And actually, there's a class of meteorites known as Isotope chondrites that look very similar to the Earth. And so, what Nicolas has been proposing is that you could actually just have an Isotope chondrite-like impactor, like Theia, and that would explain the similarity between the Earth and the Moon in the isotope ratios. But in order to do that, you still need to leave the tungsten isotope problem up to chance. It basically is that there is a chance that you would end up with the right timing of core formation, the right mixing between the materials. You'd end up with the same tungsten isotope composition, but it's relatively it's chance, and we don't like leaving things up to chance. And so this hasn't really gained acceptance as a total solution to the problem, although it is probably an important part of it. The second is that there was a suggestion by Palavin and Stevenson that you can actually try and mix material between the lunar disk and the Earth after the impact. And it's just very hard to do that because it's a very dynamic situation. And if you want to mix material across, you typically end up transferring mass and momentum because you have to transfer so much material in order to erase the isotopic differences to the level that we see. The third, which is really ingenious solution to it, which is to say, okay, so we've been focused on one potential impact. Let's get rid of that. Let's have multiple impacts, and you end up building up the Moon bit by bit from each of these impacts, and the debris sort of averages out, and so you inherit the composition of those building blocks and sort of iron out the isotopic differences. This is really interesting. It's probably an important component of dynamics, but there's sort of large parts to be worked out. Now, the final suggestion, which is particularly important for what I'm going to talk about today, is that it was proposed in 2012 by two different authors that actually you could overcome the isotopic similarities if you relaxed one of the constraints that we've been using to constrain the canonical impact. And that is that if we were to change the angular momentum of the Earth-Moon system after the impact, you could actually really explore a much wider range of different potential impacts. It was found that there's a range of different impacts. There were two separate groups that were investigated at the time. One was that very rapidly spinning Earth and small fast impactor simulation that I showed you before. Another was by Robin Knupp, which was two sort of half-Earth mass bodies colliding together, where those impacts are so much more energetic, so much more dynamic. They actually lead to a lot more mixing between the material. Actually, you end up making a much better mixture of the impactor and target material, and so explain the isotopic similarity by sort of a mechanical mixing. And after the impact, what you have to do is then you have to transfer angular momentum from the Earth-Moon system to the Earth-Sun system. And actually, there's now been various ways that have been found to do that. Originally, it was proposed by an advection resonance, which probably is a little too sensitive to work in its totality. But then Jack Wisdom and Tian came up with the idea that you also have a limit cycle. Mattia Chuk, myself, and others also have investigated something called a class plane instability. So there's a number of different mechanisms to actually transfer angular momentum away from the Earth-Moon system and basically pass it to the Earth-Sun system, so that you basically shove the Earth out a little bit in its orbit to absorb the angular momentum from the Earth-Moon system, which reduces the Earth's rotation rate and allows you to explore this much, and then sort of reproduces the present-day Earth-Moon angular momentum. But back in time, when the Moon first formed, the angular momentum was much higher, which allows us to explore this much wider range of impact parameters. Now, as written in 2012, these impacts are not really caught on because they require very specific impact parameters to get you just the right amount of mixing between the impactor and target. but we'll come back to this in a second. So psychologists assure me that you enjoy a story much more if you already know the ending. So what I'm going to try and show you today is a new model for moon formation, which is based on the idea that giant impacts, particularly high energy giant impacts, actually produce a different type of planetary structure, which we've named as Synestia, which is a kind of continuous fluid body. This body is initially so large after the impact that as it cools, condenses, the moon actually forms inside the vapor of the Synestia, inside the vapor of the Earth. And so naturally acquires both its composition and its moderately volatile element depletion. And then after the impact, you have angular momentum transfer from the Earth-Moon system to the Earth-Sun system in order to reproduce the Earth's current Earth-Moon sort of current orbital properties. And so, so this is the sort of story I'll be telling you today. But obviously, the first question we're going to ask is, what is a Synestia? Right? I've just thrown out this new word. You have no idea what it means. And to ask that, I'm actually going to ask a much more fundamental question, which is, what is the structure of a hot, rapidly rotating planet? So what I'm going to show you is a series of different planets. They all are Earth mass, so they're not going to change in their mass. And what I'm going to show you is our cut-throughs of the planet. So this is sort of a slice through through the middle of the planet. The pole, the rotation axis is here. And what you're seeing is pressure contours. So don't worry too much about the contours. What we're going to be mostly concerned with here is the outer shape of the planet. And these planets are calculated using the same sort of method we use to calculate the giant impacts. It's sort of called smooth particle hydrodynamics. And that's just to be able to give us ease of comparison between the impacts and these simulations. But the one I'm showing you here is basically what's known as a magma ocean planet. So it's if you melted all of the Earth, but not too hot, a couple of thousand Kelvin, it's fine. I mean, you wouldn't go swimming in it, but it's fine. And it has an angular momentum that is equal to the total angular momentum of the Earth-Moon system. So it's rotating with a period of about 5 hours. It's a little bit squashed. The polar to equatorial radius is about 0.9. But what I'm going to see is what happens if I start heating this planet up. So if I start dumping more energy in, so what we're going to do is increase the entropy. It's everyone's favorite parable. But basically it means it's getting hotter. And what we can do is we can increase the entropy until the point that the whole thing is just huge. The increasing energy basically means that the planet begins to vaporize, and you effectively end up with what is a silicate gas giant. It is vaporized. It's silicate vapor on the exterior. There's no surface to it because you go straight from vapor to supercritical fluid to molten rock at the core mantle boundary. So if you dived in, the first surface you would hit would be the core. But in all instances, it kind of still looks like a planet. It's still spherical. And if you put it, you'd be like, wow, that's weird. It's very bright. Looks like a star. But you would probably still recognize it as a planet. But it gets a bit weirder if we start looking at do the same experiment with a planet that's rotating a lot faster. So this is a body that has an angular momentum that is about 2.5 times the present day Earth-Moon angular momentum. And like that planet that we saw in simulation before, this planet is quite squashed. Its polar radius is about 1.5 to 2 times, its equatorial radius is about 1.5 to 2 times its polar radius. So it's more like a flying saucer than a sphere. And what I'm putting on the bottom here, because it'll be useful for us as we go along, is a plot of the angular velocity as a function of distance. And I'm plotting all of the mantle here. And so the way this simulation mechanism works is the mantle is divided up into little pieces. So there's actually a series of blobs, each representing a little mass fraction of the planet. And you'll see a bit more of them later. But they're all here. So you're all rotating with an angular velocity of about 7 times 10 to the minus 4 radians per second. And for reference here, this red line is a Keplerian orbit. So that's the angular velocity you would be at if you were just in orbit around the Earth. So this is, you can plonk the International Space Station, all of the satellites on this line. That's how fast they'd be rotating at a given distance from the Earth. So again, let's play this experiment. What happens if we heat it up? Well, what happens here is then quite different. It doesn't just continue to puff out as a sort of a ellipsoidal body. What happens is it actually puffs out to the point that the outer edge of the body intersects this Keplerian orbit. So it can't remain as a single co-rotating planet anymore. The outer edge has to be slower. It kind of goes into orbit around itself. It's still one continuous body, but the outer fraction, what we call the disk-like region, has sort of a slightly sub-Keplerian orbit, and then you have this inner co-rotating region. And we can continue to, and we called, this isn't really a planet anymore. It's not a single co-rotating planet as we thought about it. So we thought we should come up with a different name for it. And the name that we came up for was Synestia, which is suggested by my colleague Matthew Chuk, so you can blame him if you hate it. It's not my fault. we had way worse acronyms going through, so you should be glad for the one we ended up on. But Synestia is basically meaning together, so syn, from the Greek together, and Hestia, who is the goddess of architecture and home, which is Earth, but also of structures. And so together, structure. So it is a planet where the inner co-rotating region, the more planet-like part of the planet, and the disk-like fraction are actually one single continuous body. And we can continue this game and continue to heat up this planet. And what we find is the planet continues to get hotter, it continues to expand, until we have something that looks quite like, I'll show you an artist rendition later. It kind of looks like a donut, sort of a bit of a squished donut, where you have a co-rotating inner region, you have this really extended disk-like outer region, but the whole thing from the core mantle boundary out to the edge of the disk is one continuous body. And we can play this game with a whole range of different initial entropy. So planets are getting hotter left to right in this image, and they're getting faster. They're rotating faster from top to bottom. Now, these are all still Earth-mass planets, but what we find is that there is a point beyond which the planet cannot remain as a single co-rotating body anymore, that it actually starts to have to become a synestia. It starts to have this part of the body that is not rotating with the rest. It's not the non-co-rotating part. And what's really interesting here is that giant impacts are very good at both getting you very hot and very rapidly rotating. And so the structures that we find in giant impact simulations are often like those in this bottom right-hand corner. They're very extended, rapidly rotating synestias. So to give you a more of a physical image of what this looks like, this is from Rod Miller, an artist rendition from Scientific American, which sort of showing one of these synestias. You have this huge sort of squished donut. It's like you've sort of grabbed your donut too hard. Thankfully, nothing's squished out the middle, otherwise we'd be in real trouble. But you sort of got this sort of structure. Technically, it's called a biconcave disk structure. And it's just very hot. The surface is actually a silicate cloud layer radiating at about 2300 Kelvin. It would be blinding. You would not want to look at it. But what had really not been appreciated is that actually a lot of our giant impact simulations ended up with a structure like this. It's just not something that we had really examined in detail because we'd always taken our simulations, processed them as if we were expecting a planet and a disk, and been very happy we got a planet and a disk, and actually not looked at the connection between those two. So I have a question. Only the moon Earth can be formed in a Synestia, question mark, or can Jupiter's moons or Jupiter be formed in another Synestia? I also appreciate, apparently, at least someone loves the naming. So it is possible. It's actually on my list of things to do is to go back and look at Jupiter. Jupiter is a much more complicated system because while it is forming, it is embedded, certainly initially embedded in the disk around the sun as well. So it's not just a single structure. You've also got all of these external dynamics. And at the moment, the simulations that we have, the planet is a dot in the middle of your overarching simulation of how material is being fed to it. And so I think at some point it'll be really interesting. I suspect something similar will happen because you'll be angular momentum limited. Like there's only so much you can shove onto the planet because you're hitting up against this limit, which we call the co-rotation limit, the limit at which you can be a single co-rotating body. But exactly how that happens is complicated. You're also being fed from the top by material, which makes it a little more complicated. But you know, there's similar dynamics as at play. It's just way more complicated situation than the giant impact, where it's like bang and you're done. Now you can understand what's left. But cool, thank you for the question. So another question. Is there a maximum mass ratio of the binary system from the Synestia process? Could a multi-moon system be formed? So in terms of the mass ratio, that's an interesting question. In theory, if you really went extreme, you could form something that was sort of tens of percent the mass of the whole body. It's very unlikely. The energies, the angular momentum you would need would be huge. Typically, we find something of a few percent of an Earth mass. So it's probably, you probably can go bigger than the moon, but it's just going to be hard. It becomes more and more unlikely to do that. But we'll come back to that topic in a second. As to the multi-moon system, yes, so absolutely you can get multi-moon systems. And actually from a normal disk, you can also get multi-moon systems. Those systems are almost always unstable. So it's a sad fact of at least Newtonian gravity, I haven't checked with any generalistic people, that if you have more than two bodies in a system, so if you had a multi-moon system, say 2 moons and the Earth, it is always unstable. And the issue with the multi-moon system around the Earth is that the moons that are a significant fraction of the mass of the moon are sort of going to collide. So typically within that, you may form the multi-moon system, but within a few hundreds of thousands of years, you'll end up them merging or one of them being ejected from the system. And actually, if you're interested in this, there's a paper by, I'm going to forget the year in the journal, but by Robert Citron, who is now a postdoc at UC Davis, who working on the idea that you can maybe form multiple, the moon by multiple impacts, actually looked at the probability of moons merging, being ejected, or forming at least temporarily stable multi-moon systems. So look into that. But yes, it is possible. They probably won't last that long. So if you go really far back, if you get a time machine, don't be surprised if you find that the Earth had a couple of moons for a little bit. Cool. Right. So that is what a synestia is. Why does that matter for forming the moon? Okay, so you've got and the way that we really try to investigate this is to not just look at the physics of making the moon, but to try and actually understand the past, the pressure, temperature, composition, time paths lunar material went through before it was sort of incorporated into the moon. And that's important because we're trying to match these important constraints of the moon's composition, and both its bulk composition, but also its isotopic composition. And so the way that we did that was to build just to adapt one of the codes that we use for giant impact simulations to actually model the evolution of the vapor envelope over time of the Synestia, and then use a series of separate calculations to try and sort of bootstrap onto that calculation to understand the paths material is going through. So on the left here, what I'm showing you is a slice through a Synestia just after the giant impact. So what we here is just distance. So this is in megameters, which is my favorite unit. So for reference here, Earth would be 6.4 megameters. Okay, I'll stop now. So the Earth it would be down here. The present day Earth is down here in this corner. It's a very small fraction of the size of this thing. And you have this very oblate flared structure, which is the Synestia. And once again here, the contours here are pressure, which will become important. And on the outside, outside this black line, the structure is saturated vapor. So it is a coexisting mixture of rock silicate droplets and silicate gas. And inside of this, it is just entirely gas, or a supercritical fluid. So no droplets except at the very surface. And what happens is that the Synestia is cooling, and it is cooling quickly. The timescale I will show you when we're looking at this evolution is in years, which for geological timescale is incredibly fast. But the surface is a cloud layer of silica droplets. That's when the structure becomes optically thin, and you're radiating at space at about 2300 Kelvin. And that radiation leads to a torrential rainfall. So if you're standing just underneath the photosphere in a Synestia, you are experiencing a rain rate that is an order of magnitude greater than any rate of rain ever observed on Earth. So you're in sort of an uber typhoon of silicate molten rock rain droplets. It's really not a place to go on holiday. It's a very extreme environment. But what is happening is that rain is that is cooling the structure, but it's also falling under gravity, being dragged by the gas, and so is a big driver for momentum, angular momentum, mass, and thermal transport within the structure. So what we did is we modified our smooth particle hydrodynamics code to try and capture some of the physics of that. We sort of parameterized the movements of the droplets and the effect it would have on the structure. We parameterized the cooling by radiation, and basically sort of saw how it evolved. Now, an important thing I should say is that everything we chose, all the you have, when you're making a simulation, you have a load of choice points. Like, what do we assume about this? What do we decide? Which parameterization do we use for this? And all the decisions we made, we tried to make them so that we would make this the quickest evolution possible. And so all of these time estimates that I'm giving you are quite firm lower limits. It's probably going to take longer than this to evolve, but why we chose to do lower limits will become apparent later. But what I'm going to show you is on the left is the evolving shape of the structure, and then you've got these two little symbols. So the black circle is to scale the mass, the size of the moon as it is growing, and then the blue triangle is another estimate of the mass and location, this sort of location of the moon as it grows, just making slightly different assumptions about how much mass of rain the moon can accrete. So the answer is probably somewhere in between these two, but these sort of give you two, not quite limits, but two example things. Then on the right, what I'm going to show you is the mass of the moon as it grows over time for these two different estimates, the black and the blue. Yes. So what you can see is as it evolves, the whole thing shrinks. The outer fractions have a relatively small amount of mass, so they cool very, very quickly. But what you can see is that the moon here is growing inside the vapor of the Synestia at pressures of tens of bars. And the body starts off with there's a sort of what we call lunar seed that starts from the debris from the impact, the sort of not vaporized debris. But you can see the moon very quickly grows. In the sort of black case, it grows in a few years and then plateaus. In the blue case, it grows for a bit longer. But what you see is that it grows, and then there's a point when the Synestia is shrinking and shrinks inside the orbit of the moon. And at this point, the moon emerges from the vapor of the Synestia as a separate body. But importantly, it spent most of its formation being cooked inside the Synestia, sort of a giant oven, effectively. And so the moon is left with its baked-in composition, isotopic similarity, while everything that doesn't go into the moon is sort of slowly cools and forms the Earth. And so, as I said, we have the moon that's forming inside the vapor of the structure at tens of bars, surrounded by bulk silicate vapor. And so there's a lot of thermal and chemical exchange between the moonlet and the vapor that is around it. And to try and understand what that would actually mean for the chemistry, we did a series of, well, I didn't, my collaborator Misha Patayev at Harvard did a series of thermodynamic simulations trying to understand the behavior or the controlling properties of bulk silicate Earth vapor. And so what he found, what he basically did is plotted out what species are stable in the condensate and in the gas at different pressures and temperatures. So this is an example, sort of isobar from his simulations. This is the mass fraction, both the total mass fraction in this dashed line and the mass fraction of each of these elements that is in the vapor at a given temperature. So when you're very hot, everything is in the vapor. Everything is vaporized. And there becomes a point known as the dew point in multi-component spaces, but it's sort of the equivalent of the condensation line for a single component system, where things start to precipitate out of the gas. And very suddenly you get quite a lot of mass comes out over an hour interval. And then you have a much longer tail where the more moderately volatile species, things like potassium and sodium, which you remember from our diagram earlier, are actually very depleted in the moon, come out over a much longer time scale. And what's important about this is because you have this quite sudden onset from very slow sort of slow evaporation on to very rapid evaporation, if you're going from colder to hotter temperatures, or condensation going the other way, is that there is sort of a natural temperature buffer. So most of the material that goes into forming the moon either condenses at the photosphere, where you're losing radiation space, about 2300 Kelvin or so, or it is left over from fragments from the impact, which are heated to a similar sort of temperature, 500 Kelvin or so. So most of the material that goes into the moon is starting down here, and so it has most of the elements in the condensed phase. But as the moon sits in the vapor of the Synestia, it gets heated up to the point that it starts to vaporize significantly, and then latent heat becomes your friend. The latent heat of rocks, you'd be surprised to find out, is huge. It's very hard to melt rock, to vaporize rock. Good for us, really. And so what happens is you can heat up the moonlet, you can heat up the lunar material up until a point where it becomes really hard to change the temperature very much. So small things, small droplets do go through and vaporize. But if you end up in a body that is, a few percent the mass of the moon or larger, it actually takes you longer than the lifetime of the Synestia to actually vaporize through this sort of this point. And so there's this very natural temperature buffer that you end up with the surface of the moonlet, or the surface of the growing moon, being sort of tied to this similar temperatures around the point where there's about what we sort of use as a metric, about 10% of the silicon in the vapor. And what is really fortuitous about this is sort of, we were two groups and we were working differently. This was, I was looking at these plots, and then Misha, my collaborator, went and showed me what that actually meant for the lunar composition. It was just one of those astounding points of sort of discovery and agreement. But what's important here is that because we're being governed by the vaporization of the most refractory, the major elements, when you're starting to vaporize the bulk of your material, most of the moderately volatile elements are still in the vapor. And so the moon doesn't actually the lunar mission ends up losing most of its moderately volatile elements and not incorporating them into the moon. And we can look about this more quantitatively, because again, I'm showing you a very similar plot to what I showed you before, which is the amount of a material in the moon relative to the what's called the bulk silicate Earth, so the sort of Earth's mantle plus crust smashed together. Now, we're going to play the double trick where we're going to doubly normalize to aluminium. So aluminium is by definition 1. That helps because we know the ratio of elements much better than we actually know absolute abundances, just as a function of how they're measured. And this gray band here is the range of different estimates that have been made for the moon. And there's a range because basically there's a lot of uncertainty. We have a limited sampling of the moon. And so depending on what assumptions you make, you end up with a slightly different range. And what we can do is we can say, okay, so we know what the temperature buffer is for this material. We know that the pressures in the Synestia are sort of on the order of tens of bars. What does that actually mean? What would the composition of the moon look like at those conditions? And what we find is that for pressures that are on the order of a few tens of bars, we actually end up with a very good agreement between the composition of the liquid that we would predict from our models and the observed composition of the bulk silicate moon. And this really is a fantastically good agreement. It was one that we were very surprised and we were not expecting, but it is really interesting that the conditions that that the moon is experiencing inside the Synestia are controlling its composition by basically baking it to a certain pressure and temperature, and that pressure and temperature equilibration is setting the composition of the moon, and a composition that sort of agrees well with what we have observed from the Apollo samples and lunar meteorites. So in one point, this model is fantastic, right? We've answered one of those big outstanding questions, the moderately volatile element depletion of the moon. That can be explained very nicely by forming your moon from the Synestia. What about the other elements of it? So Synestia forming impacts are helpful in two ways for trying to understand why the Earth and the moon have such similar isotopic fingerprints. So firstly, Synestia forming impacts are much more energetic than the canonical impact. So during the impact itself, you end up with a substantial amount of mixing. Also, tens of % of the mass of the Earth end up being vaporized in the outer regions of the planet, and so are being mixed by exchange of droplets and material and a sort of return flow of gas. And so actually you sort of further dilute any differences by mixing a large fraction of the outer portion. So as the moon is being baked, it's being baked inside something that already has similar isotopic composition to the Earth, and so it inherits the similar isotopic composition. Now, an important caveat, this is not necessarily a silver bullet for explaining the isotopic fingerprint, this isotopic similarity between the Earth and the moon. You still probably need the impact and the target to be relatively similar. And what relatively similar is something that's the point of active research. But it definitely makes it much easier. You're not looking for identical, you're looking for similar in terms of the impact and target's isotopic fingerprint. And finally, the last of our sort of previous problems is the mass of the moon. Now, with these high energy, high momentum impacts, you eject a lot of mass into orbit. And so actually there's a large variety of impact events that can produce a synestia that is large enough to produce a lunar mass moon. And actually how large a range that is, it requires us to understand a little bit better some of the dynamics that's happening in a synestia. There's a whole load of future work to really nail that down. So in conclusion, we are proposing a new model for lunar origin. There are a range of giant impacts, not just the types that were proposed in 2012, but a much wider range of impacts that need to be high energy, high momentum impacts that can basically trigger the Earth to become a synestia and trigger the steps for the formation of the moon. In a suitable synestia, the moon forms within the synestia, surrounded by tens of bars of silicate vapor at several thousand Kelvin, and that baking sets the moon's moderate volatile element composition and gives it its terrestrial-like isotopic composition. Now, after the impact, a mechanism, take your favorite mechanism, is needed to transfer angular momentum from the Earth-Moon system to the Earth-Sun system over time. And so through this, we can naturally explain both the isotopic, physical and chemical, isotopic and chemical composition of the moon, its physical, its mass, and the orbital properties of the Earth-Moon system. And really, our model sort of moves the requirement for moon formation from a very specific, quite narrow range of impact parameters to just needing to be able to form a large enough and suitable synestia from which the moon can form. Thank you. If you have any more questions, please shoot.
Yeah, thank you so much, Simon. I see any question there? Not yet. Maybe ask your question. There seems that you have a very perfect model, a perfect solution, and then you have nothing more to do, right?
No. So yes. So the simple idea is great. There are lots of complicated elements that make it a lot more complicated. So for one of the sort of key relations to the chemistry, for example, is assuming that the composition of the moon was completely reset inside the vapor at the tens of bars pressures and several thousand Kelvin. In reality, it probably is not perfect. You definitely get mass that wasn't accommodated there. So you actually are accreting mass from a variety of different locations, a variety of different pressures and temperatures, and actually trying to understand what fraction of mass comes from each of those areas, for example, is very difficult. You need to understand multi-phase physics over planetary scales, multi-phase, multi-component systems over planetary scales. And that's just from a modeling perspective very, very hard. And so it's something that's a challenge for both synestias and sort of more traditional lunar disk models. But I think, yeah, this is a wonderful framework. It works surprisingly well in its sort of simplicity, but actually there's a lot of very complicated dynamics that may spoil the party. So there's definitely a lot of elements to work on. And really what we'd like to come up with is some sort of more tests that we could actually make some predictions about, or sort of more constraints we can use to test it. So actually a lot of what I'm looking at now is actually looking at what happens to the moon afterwards. Sorry, the Earth afterwards. And actually, because if you start from a canonical situation, or if you start from a synestia, you actually end up having quite a different post-impact evolution from the Earth. And so the idea is whether we can actually see some evidence for that in, say, the deep mantle or in the Earth's earliest crust, for example. So I think there's different avenues of evidence we'd like to try and explore to try and be able to make some more predictions rather than just trying to match the observations we already have.
Yeah, seems that because the result justify the assumption, initial assumption. Because one of the very important assumptions you have is that the Earth has to be rotating very rapidly at something like 2 to 3 hours, and that has to do with whether there's a reasonable number for accretion, because for other planets like Mars and so on, they are all rotating at much slower than 2 or 3 hours.
Yeah, it's interesting. So the advantage of the Synestia model is that there's no requirement for the pre-impact rotation rate. So you can actually, there are many situations that work when the pre-impact Earth is not rotating at all. You can actually do it you just need a slightly larger impactor. You need something that's probably about 2 or 3 times the mass of Mars in order to do that. So it's sort of a perfectly, the pre-impact rotation, which is a problem for like the Chuck and Stewart 2012 model, is not so much of an issue for anymore. But you're right. The difference in rotation rate between the bodies is a really interesting one, and in some ways it's a bit weird because it has probably a stranded embryo in the sense that it never really experienced a very large impact. People talk about a giant impact on Mars to explain the crustal dichotomy, but there's a very different scale of giant impact. What is one person's giant impact is another person's moderately large. So it wouldn't have really significantly wouldn't have affected its rotation rate to the level of the sort of giant impacts we're talking about for Earth. Now, Venus is a really interesting one. Why Venus doesn't have a moon, it doesn't have, is rotating so slowly and yet doesn't have a moon, right? If Venus had a moon, it was rotating that slowly, we'd be fine. So did Venus have a moon? Has it lost it? If Venus had a moon-forming type impact, but earlier, it is possible that if there was enough bodies flying around at the time, you would actually have kicked that moon out of orbit. So you'd have slowed Venus's rotation, but actually ended up losing the evidence, as it were. So Dave Stevenson quite likes this idea. I think he calls it the moon ratchet. If you have multiple flypasts of a Venus moon system, you can actually very effectively drain angular momentum from the system. But yeah, no, the comparative planetology element is really fascinating. We have the one Earth. It's the only thing we have with a large moon. Unfortunately, Earth-sized things with moons, like the moon, is potentially never going to be detectable in exosystems, or certainly is definitely not going to be detectable at least for the next several decades. So I think one of the things I want to try and do is take what we're working on and extend it to look at larger bodies. Like, do you end up with similar systems? Do you end up with synestias with larger planets? In theory, the scaling would say yes. I actually need to sit down and absorb the computing time to run those simulations. And in particular, actually, one of the things that I'm hoping for is that in water-rich systems, so for the Earth or Earth planets, like the Synestia cools within a few thousand years. And so the chance of actually detecting a terrestrial, like rock-based Synestia is really low. But if you have a planet that's an ice giant and it undergoes a significant energetic collision and ends up forming a Synestia, that could last for tens to hundreds of millions of years. And so there is the outside chance that you could actually detect a Synestia in a young system. And that would be a huge opportunity to study not the Earth Moon system, but a similar system, and give you a constraint on accretion and also on the dynamics of such a structure. But there's a lot of uncertainties in observing young stars, so we may not get to do it anytime soon.
Yeah, since you mentioned it, Ida recently has a paper, maybe a year ago or 6 months ago, about the formation of the Uranian satellite system. And he also talked about basically all the water first being all evaporated, and then later recondense. And so that scenario is a bit like what you have. And Okay, good. So you're going back there, Bristol, to what? To start a planetary science group?
So I have what's known as a NERC fellowship. So there's the Natural Environmental Resource Research Council. I always forget which words go in which order. But this is it's a 5-year sort of fellowship for me to do research, and I can start my own group. It's not a permanent position, but typically leads to that sort of So it's really nice. It's wonderful to have such a long time to really explore some topics. So a lot of what I'll be working on is looking at the origin of atmospheres and how, yeah.
Yeah, wonderful. And we wish you best of luck, everything.
Thank you.
Successful. And then sometime we might check up on you at Bristol,
Yeah, no, absolutely. You're welcome to come visit.
Okay, great.
But yeah, no, thank you so much for the invite.
Thank you so much. Yeah. Have a good trip back.
Enjoy the rest of the series.
Yeah.